we've been looking at internal flows. Okay. So we observed that there is no reference velocity and there is no reference temperature. So we define the mean or cup mixing temperature, which is given by 2 by r naught square integral 0 to r naught u r dr, and similarly we defined a cup mixing temperature, which is, does anyone remember, 2 by um r naught square integral 0 to r naught u times t times r dr. Okay. So that is the cup mixing temperature or the cross sectional average temperature, and that is the cup mixing or the cross sectional average velocity. Okay. Now we said that there is the temperature profile is similar. So we are going to show today what is meant by similar and how to see it, how to see that the profiles or the temperature profile in the fully developed regime is similar. So we said fully developed regime temperature profile is similar. Okay. So suppose, so here is a tube. Okay. So for both the cases, so we can make a general representation that the temperature of the exterior surface of the fluid of the tube is Ts of x, where Ts is the surface temperature. Now if it is constant flux, then the surface temperature can in principle vary with the x position, if this is x direction, and if it is constant temperature, then it does not change with position, right. So now if I want to find the temperature distribution, okay, so I want to find the temperature distribution inside the tube, let us say in the fully developed regime. Okay. So what will be the general functional form? So remember the model equation. So what are the processes which are, supposing here is my fully developed regime. So what are the processes which are acting here? You have diffusion and you have convection, right. Is it linear with respect to temperature? So we assume there is no heat generation term is 0. So it is linear with respect to temperature, right. So what will be the functional form of the temperature as a function of r and x, if this is r direction? Yeah, what will be the functional form? I am not solving the equations. What will be the functional form in which you will get the solution? Some function of r and some function of x, right. So it is by separation of variables you should be able to get two functions. It will be a product of two functions. In each of these functions will be, one will be function of the radial direction, one will be function of the axial direction. Okay. So therefore the general form of the solution will be Ts of x. So if we assume that there is heat that is being supplied from the external region to the fluid or from fluid to the surface, so the general solution will be Ts plus or minus some function of x and some function of the radius, right. So that is the general form of the temperature distribution, right. The upper limit is Ts if the heat is being supplied from the surface to the fluid, and the lower limit is Ts if it is vice versa. Okay. So that is a function of x position if it is a constant flux case, and Ts of x is constant for constant temperature case. Okay. So this is the general functional form. Note that we have not solved anything, we have just observed what is the general functional form of the temperature profile. Okay. So from here, oh sure you can, because if there is no heat generation, if you look at the structure of the equation, it's linear in temperature, so you should be able to separate. So therefore, we can rewrite the functional form as T of r comma x minus Ts equal to plus or minus f of x into g of r. Okay. So now I want to rewrite this as, I just want to rewrite it as Ts minus T equal to minus plus f of x into g of r. Okay. So all I have done is I have taken T on the other side and the function on the left hand side. So once I do this, I can introduce the averaging property here. So now if so we know that Tm, which is the average temperature, is 2 by um r naught square integral 0 to r naught ut r dr. Okay. So the objective is I want to find the mean temperature. Remember I told you that the mean temperature or the average temperature and the local temperature, there is some similarity between them, and therefore we can actually see that the temperature profiles are similar. So we are going to see that in a little bit more rigorous way as to how it is similar. So suppose I want to find out Tm from this expression, so I can integrate 0 to r naught 2 by um r naught square Ts of x u into r dr minus integral 0 to r naught T into u into r dr. Okay, that's equal to minus plus 2 by um r naught square integral 0 to r f of r naught f of x into g of r into u into r dr. Okay, so that's the functional form. So from here, so Ts is not a function of the radial position, it's the wall temperature, right? So I can pull this out and the integral is nothing but um. Um itself is 2 by r naught square is already there in um, so this is Ts of x minus Tm of x. Okay. So remember that um is 2 by r naught square into integral 0 to r naught u r dr. Okay. So that goes away, and on the right hand side you will have minus plus 2 by um r naught square. F of x is not a function of the radial position, so that will be integral r naught g of r u into r dr. Okay. So now if I divide these two expressions, you see there is an expression here which is Ts minus T, that is the difference between the surface temperature and the local temperature, and here is the difference between the surface temperature and the cup mixing temperature. Okay. So now if I divide these two expressions, minus T divided by Ts of x minus Tm of x, so this is both function of r and x, right. So now if I divide these two expressions, what you see is something very interesting. So you see f of x g of r divided by 2 by um r naught square into f of x into integral 0 to r naught r dr. Okay. So all I have done is I have just divided these two expressions, and so interestingly the functional form will actually cancel out. The x dependence will actually cancel out in this ratio, and therefore this ratio is not a function of the x position. Okay. So let me explain again. Look at the right hand side carefully. F of x g of r divided by 2 by um r naught square, f of x comes out and its integral of gr multiplied by u. Okay. So that is the cross sectional average of the function g. So f of x will cancel out. So you will see that this ratio Ts of x minus T of Rx, where the local temperature is now a function of both radial and the axial position, And not just that, the surface temperature and even the cup mixing temperature, both of them can be a function of the axial position. But irrespective of that, that's an important result. Irrespective of that, this ratio is not going to be a function of the axial position. So that is what one means by a similar profile. What it means to say similar profile is that Ts minus T, the profile that you will get for Ts minus T and that for Ts minus Tm would be exactly the same in the x direction. So the profile that you will get for the difference in the surface temperature and the local temperature and the difference in the surface temperature and the mixing cup temperature, that difference will be the same for at any location in the fully developed regime. So as a result, this ratio is not a function of the axial position. So that's an important result. It's very similar to what we got in the momentum boundary layer, where we said that the velocity profile doesn't change. So here the correct statement is that if I define a new variable, new dimensionless temperature, which is Ts minus T by Ts minus the cup mixing temperature, so that dimensionless temperature is now independent of the axial position. Okay. So this is a fundamental difference between the momentum boundary layer and the thermal boundary layer in internal flow case. So it's not the temperature profile which is not changing, it's the dimensionless temperature profile, it doesn't change with the axial position. So this observation actually can lead to some really interesting and intuitive results, which is what we will see in a short while. So this means, so if T star Ts minus T by Ts minus Tm, so I am just removing the functional, but we should always assume that Ts is a function of position if it is a constant flux condition, and Ts is constant if it's a constant temperature condition. Okay, and so that's not a function of the axial position, which means that dt star by dx is 0. Okay, so that's the first observation. So it's the gradient of the dimensionless temperature is 0 and not the gradient of the actual temperature. Okay, and in fact the definitions that we have used in all through this course, we have used a certain form for non-dimensionalizing temperature, and that really comes from this idea that using such a type of a dimensionless quantity for temperature, it actually helps in understanding the problem better and it gives much better insights. So supposing now I take d by dr of T star, okay, d by dr of T star, is that a function of the x position? No, T star is not a function of x position, therefore this is also not a function of the x position. Okay, so now dt star by dr is nothing but minus dt by dr divided by Ts minus Tm. So all I have done is I have differentiated the dimensionless quantity. Okay, so Ts is not a function of radial position and Ts and Tm both are not function of radial position. So dt by dt star by dr is nothing but minus dt by dr divided by Ts minus Tm. So that's not a function of the axial position. What is this form? What is this ratio minus dt by dr by Ts minus Tm? It's a form that we have all seen. The heat transport coefficient has a similar functional form, right? So what is the definition of heat transport coefficient? Heat transport coefficient is minus k dt by dr at r equal to r naught divided by Ts minus Tm, right? So that's the heat transport coefficient by definition, right? So now because this ratio is not a function of the axial position, this ratio is also not a function of the axial position. Okay, so this is also not a function of the axial position as long as the properties are constant. If k is constant, so we put a subscript f, it's the conductivity of the fluid. So if kf is constant, then the heat transport coefficient is not a function of the axial position in the fully developed regime. So that's an important result. So we get an important insight. So that's an important insight into the problem. So note that we have not solved the equations, we have only looked at the structure of the equation, and we have looked at what is going to be the profile of the dimensionless quantity, and from that we are able to derive an interesting insight that the heat transport coefficient in the fully developed regime is not going to be a function of the actual position. Okay. So which means that h by k is not a function of the actual position. Okay. So this provides an excellent framework, okay, this provides an excellent framework for actually comparing the transport properties for different fluids. The conductivity of different fluids are different. So this provides a very nice framework for comparing the properties of heat transport for different fluids which will have different conductivity. Okay. Now as a result, if I draw a plot of x versus the heat transport coefficient for a fixed kf, okay. So supposing if this is my fully developed regime starts at that location, so the heat transport coefficient is constant, it is not a function of the actual position. What about this region? Will it be higher or lower? What would you guess? We'll see it in a little bit more rigorous way what will be the nature of the heat transport coefficient in that location, but what would you guess? Will it be higher or lower? So I'll give you a hint. So Q, the flux of heat transport, the local flux of heat transport is defined as H into Ts minus Tm, right? So the surface temperature minus the reference temperature, right? So that's the definition. Now can you guess? So let's say constant flux condition. Yeah, it will be higher. Why? Okay, so the temperature gradient will be smaller in the entry region. So this is what is called the entry region. So the temperature gradient is going to be smaller in the entry region, and therefore in order to maintain constant flux, the heat transport coefficient has to be higher. Okay, so that's the profile of heat transport coefficient with respect to the axial position in the tube. Okay, we can see this in a much more rigorous way. So suppose I want to find out, so the exercise is now to really find out what is the mean temperature. Okay, so if I know the mean temperature, there are lots of things that I can actually estimate. Okay, so before we go and find out what is this mean temperature, let's see if we can find the relationship between the mean temperature and the actual local temperature. Can we? Is there any relationship between T and Tm? Because we say that Tm provides a way to scale the temperature, which leads to an important insight that the non-dimensional temperature profile does not change with the actual position in the fully developed regime. So which means that there must be a relationship between the two. So can we find out what that relationship? So T star is Ts minus T by Ts minus Tm. Okay. So remember that we are not solving the equation, we are not even attempting to solve the equation as of now. Without solving, what is the maximum piece of insight that we can get? Okay. So now if I take the derivative of this with respect to x, what is that? That should be 0, right? T star is not a function of the actual position in the fully developed regime, and so that should be equal to 0. Okay. So that will be Ts is a function of position, Tm is a function of position, and T is a function of position, right? So we can now write this as 1 by Ts minus Tm minus 1 into dt by dx, okay. So that is the x derivative with respect to local temperature, plus, okay, we can take a derivative with respect to the temperature Ts plus Ts minus T divided by Ts minus Tm the whole square into dTm by dx plus Ts minus Tm minus Ts minus T divided by Ts minus Tm the whole square into dTs by dx, okay, and that should be equal to 0 because the dimensionless temperature is now independent of the x position in the fully developed regime, and therefore this derivative is 0, and therefore so that this gives you an expression which relates the gradient of the cup mixing temperature and the gradient of the surface temperature with respect to the gradient of the local temperature.